Good morning, good afternoon, good evening, good night, depending on your time zone. Hello, my name is Patrick Gavigan, and on behalf of my co-authors, I have the pleasure of presenting our paper Toward Campus Mail Delivery using BDI. BDI being, of course, short for Belief, Desires, and Intentions, symbolic-based reasoning system, where an agent performs reasoning based on a set of beliefs, which can be based on perceptions of its environment, reason about those beliefs, decide on what action to take, and then perform actions to get towards a set of goals or desires. A lot of history in this type of work uses very much grid-based environments, like what we see on the left here. And very interesting research where we can see the inherent social properties of multi-agent systems using BDI, as well as the fact that these agents can be very adaptable and can adjust to changes in their environment very nicely and drop plans and based on changes in context. But we wanted to look at this from the perspective of real-world robotics. For example, what we see on the right, which is our robot. And we wanted to look at this from the perspective of an autonomous mail delivery system through the tunnels at Carleton University. Example of those being in the lower figure there. And so just giving you a little bit of an introduction of what we're going to talk about today. I'll talk a little bit about some background about BDI and robot operating system, which is what we're using, and a little bit of related work before digging into our hardware configuration and our software architecture, as well as a little bit of how things work from the perspective of perceptions and actions, and then the agent behavior. I'll give you a sample of the robot in operation. Big question being, can a BDI system work on an embedded platform? I'll give you a preview to the answer. It's yes. And some evaluation before summary and conclusion. And so for BDI system, or Belief, Desires, Intentions, we're focused on the use of JSON, which is a fairly popular BDI system. BDI being actually an older type of reasoning system, comes out of cognitive science in the 80s, mid to late 80s, and then really adopted by agent-oriented systems people throughout the 90s and then into the 2000s. There have been a number of different implementations of BDI. Our focus here will be to use JSON just because of its popularity. It uses a syntax called agent speak, where you have typically a triggering event, a context, and a body when you define various plans for your agent to operate. And so looking below on the left-hand side of the slide, we can see we could set in real agent speak code a destination such as post 1. And then we could have a rule for defining using implication, similar to the prologue syntax, that you're at destination based on beliefs about destination being at some point destination, which would be defined through unification, and that you have a perception about post point that you've arrived at, which also unifies to the same destination. We have a plan which triggers on go to location as something that you want to achieve, and that plan executes the action of drive stop when you have the context at destination. Looking to the right, we have a robot operating system. Some of you may be familiar with ROS. It's excellent for distributed systems where you can define a set of nodes which publish and subscribe to various topics. And so what we wanted to do was make our agent reasoning system work with the existing ecosystem of software and robotics that support ROS. There's some related work out there, some interesting stuff. For example, the Codera Avatar and Automated Wingman coming out of Australia, where they actually used a BDI agent implemented with Jack to fly UAV, shown in the figure. There have been other efforts to fly UAV, for example, with Giacomo, and there's other efforts for using ROS with JSON, such as Race and Jacka-ROS or JROS, as well as robotics effort with with BDI reasoning systems such as Profeta and Argo, and efforts in real-time BDI and simulated approach, some of our own work with Savvy. Some more information about those related works are available in our paper. So looking at our, getting into the teeth of our hardware setup, this is a first iteration robotics implementation, not the final iteration. We really wanted to just sort of get at the low-hanging fruit to see what sorts of problems we would run into and look at the feasibility of actually getting BDI working with real-world robotics. And so we used a Raspberry Pi 4 on top of an iRobot Create 2, which is basically the Roomba vacuum cleaner without the vacuum cleaning component. We integrated that Raspberry Pi such that it was running off of the batteries on the robot, and added a line sensor underneath as well as a camera for detecting QR codes for navigation. Reason being that we don't have access to GPS or any type of GNSS signals in a tunnel type environment. This being a first iteration, as you can see on the right, we have the robot viewed from above, from the side, and underneath, where you can see the line sensor in the vacuum cleaner bay. From a software architecture perspective, so we could think of this as sort of a layered architecture using what we're calling SavvyROS BDI as the top layer, where we've integrated the JSON agent speak reasoning system with ROS. What happens here, and this is programmed in Java using ROS Java, where we subscribe to perceptions and an inbox for messages, and we publish actions and our outbox for outgoing messages to ROS. We also define our application node, where we have various translators for perceptions, our inbox, outbox, and actions being translated out. That really acts as sort of like a middleware between the various hardware actuators or sensors or other ROS nodes that we might be interacting with. In our case, the Create Autonomy package for interacting with the Roomba. We also wrote our own Python-based driver for translating those Roomba, the appropriate Roomba messages to perceptions and actions back into so that the Roomba could understand them. Also drivers for the camera for reading QR codes, as well as for the line sensor. And as I said, all of this runs on a Raspberry Pi 4. In terms of perceptions and actions, our line sensor driver generates perceptions based on if the line is in the center, the left, or the right of the sensor, or across, or just simply not seen at all. We have the camera generating generating perceptions in the form of post point with your current and previous location QR codes that you've detected. There's a user interface using an Android app where a user could pass the message in the form of destination and what destination you wish the robot to go to for delivering mail. We also have battery information in the form of battery low or battery okay, so that the Roomba can make a decision with regards to how much power is remaining. And then from the translation perspective for actions, driving forward or turning left or right, or stopping, and then docking or undocking the robot from a charging station. So looking in at the image in this slide, we can see an example map that we're working with a variety of post points where we would want the robot to go. And robot navigating by following the line, as well as a docking station. Now what we've done is broken this up into various layers of goals that the robot could achieve. As part of navigation, though, we also use some rules. For example, we have at destination or destination right, which is how we encoded the map. And so as the robot moves around the map based on the perceptions, you would have from the post point that you're receiving from the camera perceptions, you would see what location you've arrived at and where you've come from, and from that, as well as knowledge of your destination, you would have destination right or at destination or destination left, etc. Our highest level objective is deliver mail, And from these, we use the go-to location goal as a sort of a sub-plan associated with that. And so based on whether or not you have mail or you've arrived at a sender location, etc., we set the objective of going to a location or delivering mail, or we adjust our beliefs whether or not we have mail, etc. Then we have going to the location, which uses the rules for destination ahead, at destination, left or right, to make the decision as to whether or not the robot needs to turn left or right or continue following the path, which is a slightly lower level goal which really handles following the line. So it's watching for perceptions with regards to line being in the center, line being lost, or using unification for if the line is to the left or to the right, and so you can adjust the direction that the robot needs to turn. Finally, with regards to the charging station, we have dock and undock. But the plan for docking, which is shown here, is used to dock the robot when you have insufficient power and have in fact arrived at the docking station. And so what we'll see here is a little recording of the robot in action. And so here we've given the robot the objective of going to the lower portion of this map, which looks like the number 4. So it's going to the bottom of the 4 to deliver some mail, which is clipped to the robot. But as you can see, as it arrives at this location, it wants to go to its final destination, but at this point it needs to drop the plan of delivering mail and instead needs to go and get some charge from the charging station, which is at the top of that number 4. And so it arrives at that location and charges the battery. We had a cut in the video there where now it's got sufficient power, it's now backed up, and now the objective of gaining additional charge on the battery is no longer applicable, and now we can again focus on delivering mail to our destination, which is that post point at the bottom of the map. So from the perspective of evaluation, as I mentioned earlier, we wanted to get a sense of if BDI was a feasible system for running on an embedded platform. And so on the left we see, well, in both figures we see the period that we measured for perception messages being passed to ROS, as well as on the right action messages being published to ROS from the reasoning system. And so what we find, or what we would expect if the reasoning system was not able to keep up with the perceptions being sent into the reasoning system, we would not expect those graphs to match. And what we instead see is a very strong set of period at 0.08 seconds and 0.02 seconds corresponding to different types of perception messages that are being generated and passed into ROS. And accordingly, we see on the action side the reasoning system generating actions associated with having received those perceptions at an equivalent period, meaning that the reasoning system is in fact keeping up with the sensor information that's being passed to it. And so from that perspective, we have a number of accomplishments. We've demonstrated that BDI can in fact drive a robot on an embedded computer. And yes, this is a first iteration, so ultimately we'd want to move towards doing real mail delivery in tunnels, which could mean moving towards doing more planning-based or search-based navigation, maybe going towards a multi-agent type system, and then moving beyond line following and QR codes and doing something more sophisticated for path following. But at this stage, we have demonstrated BDI for an embedded system. We've demonstrated the SavvyROS BDI framework and that mail delivery behavior can be accomplished, albeit using line following and QR codes. All of this being successfully integrated with the Raspberry Pi on the iRobot Create 2. And with that, I'd like to thank you for your attention today, and I'm available to answer questions. Thank you very much.